Okay, good afternoon, everyone. So we're very happy today to have Jenny Wilson from the University of Michigan Ann Arbor, who will tell us about representation stability. Jenny, please.
Wonderful.
You agree to recording?
Did I succeed in agreeing to recording?
Here you go. Great. Yes.
Wonderful.
Yeah. Please go ahead.
Yes, thank you. Thank you so much for the invitation to speak today. I've just shared a link to my Jamboard in the chat. If anybody would prefer, they can access the whole set of slides there as I speak. And great. So today I will be, I think I'm sharing my screen. Somehow it's not, whoops, didn't mean to do that. It's not, Zoom is not behaving the way I was expecting it to. Can everybody see my first slide? Yes, wonderful. Thank you. So excellent. So today I will be trying to give a pitch for the subfield of representation stability, which has been developed over the last 10 years. With a focus on how we can use it to illuminate something about the structure of configuration spaces and braid groups. Okay, so to that end, let me define or remind us of the definition of configuration spaces. I am going to let M denote a topological space. For my purposes, M is usually a manifold. And throughout this talk, I'm going to write F sub n of M to denote the ordered configuration space of M on n points. And here's the definition. This is the space of all ordered n tuples of distinct points in M, topologized as a subspace of the n-fold Cartesian product. And so, right, per this definition, one way I might think about these ordered configuration spaces are, I take the n-fold Cartesian product and I delete the so-called fat diagonal. I delete all of the points where two or more of the components coincide. And so from this point of view, these configuration spaces are examples of complements of subspace arrangements. And here's a picture of, I guess, the simplest possible example of a configuration space. So I've taken my interval, the interval 0, 1. And so it's the ordered configuration space on this interval on 2 points is what I get if I take the two-fold Cartesian product, I take the square, and then I delete the diagonal. So in this case, the configuration space is just two contractible components. Another way I might think about these ordered configuration spaces is as a space of functions, a space of embeddings of a discrete set on n points into the space M. And from this point of view, I might visualize a point in my configuration space, something like this, where I have here, I've drawn a picture of the n labeled components in my point in the configuration space. And let's see here. So from this point of view, I can think of my configuration space of the interval as a space of pictures like the ones that I've drawn here. And we can understand the topology of this space from this perspective as well. So here we see this bottom component is going to be all the configurations where the second component, the particle labeled 2, is on the left. And this upper triangle is all the configurations where particle 1 is on the left. And we, I guess, can understand from this perspective as well that this space cannot be path connected because there's no way that I can slide this particle labeled 2 pass the particle labeled 1 in the configuration space without some sort of collision of particles that exits the configuration space. Okay, so great, that was the warm-up example. And let me advance to the next slide. Again, a reminder of the definition of the configuration space. These are distinct n-tuples in M. Okay, so it's not too hard to check that in general, if we look at the configuration spaces of an interval, then their connected components are going to be indexed by permutations of n. So here is a picture of a configuration in the connected component that corresponds to the permutation 2143. And it's not hard to check that each component is contractible. So, okay, great. So we fully understand the space of ordered configurations on an interval. In contrast, things get a lot more interested when we start to study spaces, manifolds M of higher dimensions. So the first example here is maybe the disk. And right, the first observation is that now the ordered configuration space of points in the disk is going to be path connected, which is not too hard to see. You can visualize that if I choose my favorite configuration and you choose your favorite configuration, then it's always possible to find a path through our space that moves the particles from mine to yours without any collisions. That said, these spaces are still extremely topologically rich, that the fundamental group of these ordered configuration spaces is going to be exactly Artin's pure braid group. And here is a cartoon picture that is intended to illustrate that if we look at a path through this configuration space, a loop in this configuration space, drawn out here like a movie, then with the time direction arranged vertically, then the result is a braid. Okay. So let me advance a slide. These ordered configuration space have a natural action of the symmetric groups that act on them by permuting the labels on the particles, permuting the n-tuples. And this action is a free action. It's a covering space action, since in the definition of these ordered configuration spaces, we have deleted precisely those points from the Cartesian product that would have had non-trivial stabilizer. And so what we get is this covering relationship here. I get a covering relationship between the ordered configuration space and the orbit space under the symmetric group action. So that orbit space is the unordered configuration space. And I can view this quotient map as taking a point in my ordered configuration space and simply forgetting the labels on the n particles. And so, in other words, this unordered configuration space of M on n points, which I will denote C sub n of M, this unordered configuration space is the space of subsets of M of cardinality n, topologized with this quotient topology. Okay. And again, by a similar argument, the fundamental group of these unordered configuration spaces in the case of the disk is precisely Artin's braid group. And it's a fact that at least in the case of the disk, or the case of most surfaces, these configuration spaces are k-pi1 spaces for the pure braid group and the braid group. So we'll primarily be in this program be interested in the homology of these spaces, which means that in the case of the disk, studying the homology of the ordered configuration space of the disk is equivalent to studying the group homology of the pure braid group. Okay. Great. So, right. So the goal of this program is to understand something about the homology of these configuration spaces. And toward that goal, I have, I guess, good news and bad news. Some good news is that it's possible to understand these homology groups in very concrete terms. So we can understand these homology groups in terms of pictures like the ones that I've drawn here. Here's a picture of a 2-parameter family of configurations. What I've drawn is supposed to represent a picture of the particle labeled number 4 running in a loop around the particles labeled 5 and 1, and the particle labeled 3 running in a loop around this piece of genus in this surface. And because these two loops don't intersect, I can run both loops, I can run both movies independent of one another. And this means that this picture represents a copy of S1 cross S1, a picture of a torus in my configuration space. And because the torus, it's a closed 2-manifold, at least up to sign, this picture represents an element in the degree 2 homology of this configuration space. So, right, the good news is that these homology classes are, in a sense, easy to visualize in very concrete terms. But unfortunately, the problem of understanding the additive relations in homology between these classes, like questions like, is this homology class 0, turn out to be very subtle. And they're so subtle that, in fact, despite the fact that there is a large and beautiful literature on the homology of these spaces, we still are not able to answer questions like, what are the Betty numbers of these configuration spaces? Like, what are the ranks of the homology groups in all but for a kind of small handful of manifolds? In general, we don't know what the Betty numbers are. So that is to say that computationally, these groups are difficult. And the key to this representation stability program is the following. We are going to fix the background space M, and we are going to package this entire sequence of homology groups for every value of n into a single algebraic object with additional structure coming from both the actions of the symmetric groups and certain topological operations that I'll define in a moment. And the extra structure that we get, that I'll define a little later in the talk, will allow us to identify some patterns in these homology groups that would not be accessible if we were just studying each homology group individually. Okay. So the context for this program are classical stability results about the unordered configuration spaces of M. And right, for the duration of the talk, I'm going to assume that M is a connected non-compact manifold of finite type and dimension at least 2. So let's say M is the interior of a connected compact manifold with boundary. And under those assumptions, it is possible to define a continuous map that I'll call the stabilization map from the the unordered configuration space on M on n points to the unordered configuration space on n+1 points. It's possible to define this map as follows. We're going to take a configuration and we're going to introduce a new particle in a sufficiently small color of a distinguished choice of boundary component. Right. So it turns out these maps extend continuously over the configuration space. And a theorem of McDuff and Siegel from the 1970s states that with respect to these maps, this sequence of unordered configuration spaces for a fixed manifold M, the sequence of unordered configuration spaces is homologically stable. So what this means is that for each fixed homological degree I, the induced map on homology by our stabilization maps is, at least for n sufficiently large, an isomorphism. Once n is at least 2i, then these homology groups, these degree I homology groups, stabilize. And so this says that even though these configuration spaces are getting increasingly complicated topologically as n grows, at least from the point of view of homology, somehow the I-dimensional structure stabilizes. And the heuristic, the picture to have in mind with these results are the following. Heuristically, what this says is that my degree I homology for my unordered configuration space is spanned by classes that we should think of in terms of pictures like this one. It says that I have at most 2i many particles that are moving around the manifold or moving around each other, and the remaining n minus 2i particles are sitting static by the boundary. So this is what degree I homology classes look like. In this case, under these assumptions on M. Okay. So,
Yes.
oh yeah, question.
Yes. Are you somehow saying that if you have sufficiently many points, then sort of generically a bunch of them are going to be in the boundary, and this is what gives us close to the boundary, this is what is going to give us stability?
Yes, exactly. That's right. So if as the number of points grows and grows and grows, then a homology class is going to look like a sum of elements where exactly that all but 2i many of those points are somehow out, quote, at infinity. They're out by the boundary component.
I see. Okay. Got it.
Was that the question, or?
Yeah, I just want to make sure I understood this step.
Yes, exactly. So this is what, if you, right, so if you think of what, at least if we visualize these homology classes in the way that I drew on the previous slide as like particles moving around in the space, then this induced, the map on homology induced by the stabilization map is just introducing additional particles out by the boundary. And so this is what a picture would look like of a homology class in the image of the stabilization map. And the theorem says that the entire, like every homology class is in the image of a composite of stabilization maps coming from a configuration on 2i particles.
Okay.
All right. So my interest is in the ordered configuration spaces of M. And I'm going to carry forward this assumption from here on out that M is now the interior of a connected compact manifold with boundary of dimension at least 2. And a question we could ask is, as in the case of the unordered configuration spaces, are these ordered configuration spaces homologically stable? Possibly a naive question. The answer is no. And we can see that this will fail even in the first possible cases. So for example, if we look at the degree 1 homology of the configurations of a disk, so in other words, this is the abelianization of the pure braid group, then what we get is a free abelian group of rank n choose 2. So this is growing quadratically with n, and there's no hope of the sort of stability that we saw on the previous slide. And we can say precisely what these homology groups are. So I can define n choose 2 loops in my configuration space for every choice of particles I and j, every pair I and j. I can define a class where particle labeled I runs in a circle around particle labeled j, let's say counterclockwise. And it turns out that these classes are additively independent and that they generate our homology group. And so, right, we see concretely that stability fails in this case. But something else that we see that is, I think, suggestive of the whole philosophy behind representation stability is that even though these groups are growing, up to the action of the symmetric group, which acts by permuting the labels, and the action of these stabilization maps T, which introduce particles out near the boundary, then the homology of all the homology groups in the sequence of configuration space on the disks is in a sense generated by this one element that comes from configurations on just 2 particles. Okay, and so the slogan is that even though these groups are growing up to the action of the symmetric group, there is a sense in which they stabilize. There is a sense in which all of the homology comes from low values of n. Okay. Great. So with that picture in mind, let's state one version of the theorem for ordered configuration spaces. In this case, again, we're assuming that M is, let's say, the interior of a compact connected manifold with boundary, dimension at least 2. And as before, we can define a continuous stabilization map on these configuration spaces where we introduce a particle labeled n+1 in a sufficiently small color neighborhood of the boundary. And so the theorem, which was proved by Church-Ellenberg-Farb in the case of orientable manifolds and then generalized to non-orientable manifolds under these hypotheses in work I did with Miller. So this version of the theorem says that if I fix the background manifold M and I fix my homological degree I, then the sequence of homology groups is representation stable if I take my degree I homology on n particles, then it's no longer true that the image of this group under the stabilization map is equal to the homology of the configurations in n+1 particles. But if I take its orbit under the symmetric group, then that will span the homology of my configurations on n+1 particles. And this pattern holds once n is at least 2i. So in this case, the heuristic that we should have in mind is as follows. This says that my homology group on n configurations on n particles is spanned by classes that we should think of as coming from pictures that look like the following. Here's a picture where all but 2i of the particles are just sitting static out by the boundary. And the growth in N that we saw of the ranks of these homology groups are explained by pictures like this one. So it turns out that these Betti numbers are going to grow polynomially in, they're going to grow polynomially in N. And that growth is explained by, they're growing like N choose 2i, they're growing like a polynomial of degree 2i. That is explained by the observation that there are N choose 2i possible ways that we could label the particles that are sitting out by the boundary. Okay. So this is a picture of this sort of stability result. And
Sorry, could I ask one question?
yeah, please.
I'm just wondering if you could give us some feeling for how non-trivial this is. I mean, I don't doubt it, but just on, due to the following fact that it seems we're essentially exchanging now the kind of the time when we quotient by the symmetric group, right? We already know from the classical results that if we kind of quotient out by the symmetric group before taking homology, right, then it's stable. That was the classical homological stability, right? And now we're saying, well, if we don't do this and it's not stable, well, so let's quotient out by the symmetric group after all, after the fact, right?
Yeah, that's right. So let me see if let me make a comment, and maybe it will answer your question, or if not, maybe you can ask a different question or repeat the question to help me understand. But one comment is that let's specialize. Instead of working with integer coefficients, let's say I worked with like rational coefficients where the same statement holds. In that case, because I have this covering relationship, this kind of finite regular covering space relationship between my unordered and my ordered configuration space, there's, by a standard transfer argument, I can identify the trivial subrepresentation of the symmetric group in the homology of the ordered configuration space with the homology of the unordered configuration space. So the component upstairs, the subrepresentation where the symmetric groups act trivially in the rational homology is identified with the homology of the unordered configuration space. So the classical results coming from unordered configuration spaces give me stability for N sufficiently large for the trivial subrepresentations upstairs in the homology of the ordered configuration spaces. And then there's lots of other non-trivial homology as well, homology with a non-trivial SN representation, which I guess is the content of this new theorem.
I see. Okay.
Did that?
Yeah, that helps. Thanks. Yes, I'll think about
Yeah.
it, but that helps. Yes.
Okay, thank you. And I'll say more about this theorem momentarily. Before I do that, I should comment that this work was all inspired by the first results of Church in 2012 and Church-Ellenberg-Farb in 2015. And since then, there has been, it has inspired a lot of work on different forms of representation theoretic stability patterns in the homology of these configuration spaces. So here is probably an incomplete list of some of that work over the past 10 years. Much of this work is focused on generalizations to, for example, broader classes of spaces M, such as when M is maybe a graph or some other situation where it's not a manifold, improve stable ranges, alternate stabilization maps, and various forms of higher order stability that detects patterns between the unstable homology in the sense of Church-Hellenberg-Farb. So unfortunately, I can't do justice to the work of all of these authors here, but I'm happy to answer questions about it at the end if anybody's interested. Okay, so let me elaborate a little bit more on some maybe stronger variations and consequences of this main theorem about stability for the homology, the ordered configuration spaces of our manifold M. These are consequences of the theorem, as I phrased a moment ago, using the algebraic framework developed by Church-Hellenberg and Farb. So let me see. So the first, we're going to again fix M, and we're going to fix our homological degree I. And right, so first of all, I've restated the theorem from the previous slide, which is a phenomenon that maybe we'll call finite generation. So this says that all the homology of all the degree I homology of these configuration spaces comes from, up to the action of the symmetric group, comes from the image of classes on 2I or fewer particles. That's finite generation. And it turns out that a first consequence of this result is that the Betti numbers have to grow polynomially, and specifically the Betti numbers for in the ith Betti numbers have to grow in n like a polynomial in n of degree at most 2I. And we saw, right, our first example of this polynomial growth in the case of the pure braid group. So its first homology is free abelian of rank n choose 2. Okay. The next consequence, and this was the original focus of the work of Church and Farb, was they proved a phenomenon that they called multiplicity stability. And what this says is that if we work with the rational homology groups, then, well, this is a rational representation of a finite group. So it decomposes into a direct sum of irreducible representations. And in the case of the symmetric group, well, the complex irreducible representations of the symmetric group are known, they're fully classified, they're in canonical bijection with Young diagrams with partitions of n, like I've drawn here. I'm using these pictures of partitions of these Young diagrams to denote these representations. And it's a fact about the symmetric group that all the complex representations are in fact defined rationally. So the same statement is true for rational representations. So it makes sense to ask the question of what are the irreducible constituents of this symmetric group representation that is this rational homology group. And it turns out that these stabilize, and the sense in which they stabilize, I've illustrated here, again, in the case of the degree 1 homology of the pure braid group. So this table shows the decomposition into irreducible representations for the first 7 values of n. And what we see in this table is that once n is at least 4, I can get from one row of the table to the next one simply by adding a single box to the top row of each of these Young diagrams in my decomposition. And so it turns out that that pattern persists. And what Church and Farr proved is that the same pattern holds for all homology groups, for all of our manifolds M, even though in most cases we do not know what this decomposition is. Okay, so that's multiplicity stability for the rational homology groups. Okay. Another consequence that they proved is that the characters of these representations are given by what are known as character polynomials. So again, as we know, if we have these rational representations of our symmetric groups are fully determined by their characters, the character being the class function that reads off the traces of the symmetric group elements acting on this representation. And what they proved is that the character, the sequence of characters, so if you fix homological degree I, we get a sequence of characters. The sequence of characters is represented by a polynomial in what they call the cycle counting functions. This polynomial is independent of n. And again, let me illustrate what I mean by this statement in the case of the degree 1 homology of the pure braid group. So in this case, again, as a representation, this is just the free abelian group on these elements that we denoted alpha sub ij. Sorry, in this case, a rational vector space. This is a vector space with basis, these elements alpha sub ij, as I and j range over all numbers from 1 to n, all distinct numbers. And so because this is a permutation representation, because I'm just acting by permuting a basis, the trace of the action of one of my permutations is just going to be the number of basis elements that it fixes. And so it's not too hard to calculate that this means that the trace of a permutation acting on these homology groups is going to be given by the number of 2 cycles in my permutation plus the number of 1 cycles choose 2. And that formula holds for all permutations for all values of n. Okay. And so the statement about character polynomials says that there exists, we don't know it in most cases, but there exists for every single one of these sequences of homology groups, an analogous polynomial in the cycle counting functions like this one. And there are stronger statements where you can bound in an appropriate sense the degree of this polynomial and the sizes of the cycles that are involved. Okay, so this is another combinatorial constraint that follows for the sequence of these sequences of homology groups. Okay. Another consequence is that it turns out in the case of these ordered configuration spaces of open manifolds, the homology is a free object in an appropriate sense in this algebraic context, which I have not yet defined. But what that implies is that, in fact, the homology, each of these homology groups can be described as an induced representation of a very particular form, induced up from certain sub-representations of the first 2i groups in the sequence. So induced up from certain sub-representations of the homology on 0, 1, 2, etc., up to 2i many particles configuration spaces. And right, again, to illustrate this point, in the case of my favorite example, which is the degree 1 homology of the pure braid group, what this says is that in this case, this homology group is equal to the following representation induced up from the homology of the configuration space on just 2 particles. So although we don't know what they are in general, there are analogous formulas for the homology groups of any degree I for any choice of manifold, satisfying our conditions. Okay, so this is to say that as representations, these sequences are heavily constrained as a consequence of this finite generation statement. Okay, and when Church and Farb were studying these configuration spaces back in around 2010, before they understood the correct algebraic framework to situate this whole problem, they started noticing kind of empirically analogous patterns in a large variety of other contexts for other family of groups. So they noticed analogous patterns, for example, in the homology or cohomology of certain flag varieties as representations of the associated Val groups, in the hyperplane arrangement complements associated to certain reflection groups as representations of those reflection groups, in the level I congruence subgroups of general linear groups of certain rings, in mapping class groups in moduli spaces associated to punctured manifolds, in the Torelli groups of mapping class groups or of automorphisms of free groups. And all of this raised the question, why are these patterns so ubiquitous? What is the underlying structure that is responsible for these particular patterns? And so Church and Farb, along with Jordan Ellenberg, answered this question as follows. They formulated the following, well, they studied the following algebraic setting and proved that it is a driver of all of the patterns that they saw. The answer is that all of these sequences of homology and cohomology groups are finitely presented FI modules. Okay, so let me define this. I will use the Church-Ellenberg-Farb notation of letting Fi denote the category whose objects are finite sets and whose morphisms are all injective maps. So this is equivalent to the category I've drawn here, where my objects are just the standard set on the numbers 1 through n. And the morphisms are generated by the standard inclusions and the endomorphisms, which are copies of my symmetric groups. Okay. And so definition, an Fi module is a functor from this category Fi to the category of abelian groups. Okay, the data of such a functor is going to be, well, first of all, I get an abelian group for every natural number. And that abelian group is going to come equipped with an action of the endomorphisms, an action of the symmetric groups. So I get a sequence of SN representations. And in addition, I get these maps induced by the inclusions. So I get maps between my SN representations that are equivariant with respect to these symmetric group actions. Okay. So great, this is an FI module. And in fact, the relations in this category mean that it's actually not all sequences of SN representations with equivariant maps are FI modules. They're more constrained than that. But in particular, this is what one of these functors looks like. Okay, so briefly, some examples of FI modules. First example is if we take the sequence of trivial SN representations with isomorphisms, that has the structure of an FI module. If I take the sequence of canonical permutation representations of the symmetric group along with the obvious inclusions, then this has the structure of an FI module. If I take, let's say, polynomials on n variables and the usual inclusions with Sn permuting the variables, then this has the structure of an FI module. And more generally, if I apply any functor, like take symmetric or alternating powers of an FI module, I will get an FI module. In contrast, a non-example of an FI module is the sequence of alternating representations of the symmetric group. So exercise, this is not an FI module. This is not a functor from this category. Another non-example, a sequence of SN representations in equivariant maps that does not have the structure of an FI module, is the sequence of left regular representations of the symmetric group with the obvious maps, the obvious inclusion maps. And the example that's most important for our purposes are the sequence of homology groups of in fixed degree I for our favorite manifold M. And so here is a picture of the action of Fi on these homology group. It's induced by the following maps at the space level. Okay, so if I have an injection of finite sets, here's an injection from the set 1, 2, 3 to the set A, B, C, D, and I take a configuration with points labeled by 1, 2, 3, then I'm going to let this morphism act by taking my particle labeled 1 and relabeling it by the image. I'm going to relabel it by B. And then here, the particle number labeled D is not in the image of this map. So I'm going to use my stabilization maps to introduce the particle D at the boundary. And at the space level, we do not get an action of Fi because at the space level, introducing the particle D and then introducing a second particle is not, it depends on the order in which I introduce these particles near the boundary. But up to homotopy, this does give me a well-defined action. So in particular, the homology groups do have a well-defined Fi module structure. Okay. And another observation that turns out to really constrain the behavior of this sequence of homology groups is the observation that, in fact, there's also a contravariant action of the category Fi that is in a compatible sense on these spaces. And this contravariant action we can see as follows. So if I have, this time I have my same morphism, this time I start with a configuration labeled by the points A, B, C, D, and I'm going to act by, sort of by precomposition, I'm going to act by, here my particle labeled B, I'm going to relabel by its pre-image, the number 1. And I am going to just forget any particle that is not in the image of this map. Okay, so we have both an action, a covariant and a contravariant action of Fi on the homology of these configuration spaces. All right. And the what Church, Ellenberg, and Farb proved is that the driver, the feature of one of these FI modules that is responsible, that implies all of these consequences that I listed earlier in the talk, these consequences like multiplicity stability of irreducible representations, the character polynomials, at least in the case of free objects, this description as a sum of induced representations of a particular form, and more generally as a quotient of a sum of induced representations of a particular form. All of those consequences are a result of having the structure of an FI module that is finitely generated. And so let me define the term finitely generated through another example. I would like to look at the case of an FI module that is given by the homogeneous degree 2 polynomials on n variables. So if I look at polynomials on n variables, that is an FI module. That sequence is an FI module. It is not finitely generated. But if I restrict to those that are homogeneous of degree 2, then I get the following picture. So I get the first piece is generated by x1 squared, the second by x1 squared, x2 squared, and x1, x2, and so on and so forth. And the key is that up to the inclusion maps and up to the action of the symmetric group that permutes the indices, this entire sequence is spanned by just two elements. It's spanned by the element x1 squared that lives in degree n equals 1, and the element x1, x2 that lives in degree n equals 2. And every subsequent basis element in the sequence is the image of one of these two elements under one of the FI morphisms. So this is one way that we can define finite generation. It's just saying that there is a finite set of elements in this FI module that, up to the action of the morphisms, generates the entire sequence. Okay. And again, a result of Church-Ellenberg-Farb is that if you have a finitely generated FI module, then it implies that list of combinatorial and representation theoretic constraints on its long-term behavior that we saw earlier in the talk. So current directions for this field, in addition to continued study of the structure of configuration spaces, some goal. Yeah, please.
I mean, so you meant in the list of further examples that you had briefly mentioned on other moduli spaces that exhibit this stability, it seems not all groups were symmetric groups, right? You had Weyl groups there. Could you say how? So how is that an example then?
Yeah, sorry. So you're absolutely right. That's right. So not all of the. That's right. Not all of those were FI modules. I mean, many of them are, but there are, which unfortunately I don't have time to get into in much detail, but there are analogous, there are categories analogous to FI that you can use to index a sequence of representations of any of these other groups. So there are categories in the case of the classical Weyl groups, in the case of many examples of reflection groups, in the case of many families of linear groups. And there are also various decorated versions of FI where you, for example, decorate the complements of the images of the morphisms. And this lets you track additional data in your maps. So there are lots and lots of variations on this setup that are being studied right now. And in some, but not all cases, there are analogous statements that say if you have finite generation as a module over one of these categories, then there's this long list of combinatorial constraints that this implies on the long-term behavior of your sequence. So, right, so yes, in that direction, I was just going to say that some of the ongoing goals of this field, the second one listed here is exactly that. It is to adapt and refine the tools of developed for studying these sequences of symmetric group representations to encode actions of different families of groups. And I think there's been a lot of interesting work, I think, in this direction, but there are still things that we don't understand for some of these other categories. And in fact, there are still things that we don't understand about FI modules. So I would say that it is ongoing work to try to develop commutative algebraic tools for proving finiteness properties of these FI modules. That once we're working in this setup, the category of FI modules is an abelian category. That means that we can tackle it using all of the tools of commutative homological algebra. And one of the flagstone results of the field, Church, Ellenberg, Farb, and Nagpal proved that whenever you're working, if you're working with abelian groups, FI modules and abelian groups, then the category is Noetherian in the sense that whenever you have a finitely generated FI module, all of its submodules are finitely generated. That's somehow the crucial result behind these big stability theorems. And right, it turns out that, as working in an abelian category, that there's a large number of tools that we're able to draw on in order to study these objects, but there are still a number of finiteness. Pardon me. There is still work to be done, I think, in refining some of the tools. Okay. And yes, thank you.
Any further questions for Jenny? So yeah, I have a question. So of course, naturally, the examples are the two disks, but in the results in the theorem, you had a general manifold. So there's no restriction on dimension or any properties of the manifold otherwise?
No, that's right. So let me go back. I need my hypotheses written here. So I need for the result to hold, I need the manifold to be connected, and I need the dimension to be at least 2. And I really do need this assumption on dimension at least 2, because otherwise, if my manifold is just one dimensional, like if I take the interval, for example, then I really don't get an FI module structure, because then it really matters the order in which I introduce new points at infinity. In that case, it is not true up to homotopy that I can introduce points in any order at the boundary. So I really do need, which is good, because otherwise the configuration spaces of the interval that we saw at the beginning of the talk would be a counterexample to all the theorems that we saw. So we really do need dimension at least 2, but there's no other constraints on dimension.
Thanks for the very nice talk. I'm wondering about the following. There's this a very interesting variant of the braid representations that one gets this way by introducing a twisting, by introducing a local system and looking at the twisted homology. Has any of the stability results that you mentioned been applied in this more general twisted case?
Yes, absolutely. So maybe this is related to what you mean, but I think if you take coefficients in a sequence of SN representations that
Yes.
has some appropriate kind of polynomial condition on it, then some polynomiality condition, then you can prove classical stability results for those homology groups with twisted coefficients from this framework.
Does this also work for, I would like to take a braid representation, actually take the dimension to be 2 and take the module to be, does that make sense? Or I see that maybe it doesn't make sense after passing to homology.
Oh, that is a good question. I would have to think about that. I think this depends on the specific representations.
All right. Yeah. So yeah, I guess it might be a hard problem. I was just wondering if anybody looked at it, but maybe the answer is no, this hasn't been looked at probably. I don't know. Yeah, all right.
Yeah.
Right.
Yeah, good. Any other questions? Okay, not, let's thank Jenny again for the very nice talk.